In this module, we'll talk about shear walls with respect to seismic forces on them. And we could be looking at shear walls with wind loading on them, but the idea of combining the performance of shear walls and seismic just seems to be a pretty efficient way to kind of look at these issues. So, a few ideas about this idea of seismic design, earthquakes, and what they do to our buildings. I think we're all familiar with the idea of the San Andreas Fault in California. Plate tectonics, as illustrated in two fault lines moving by each other. They build up forces, they get released, and that results in an earthquake. These happen in many cases deep under the soil. And so we have these two terms, one that I wasn't familiar with. We have E, the epicenter, the ground point where an earthquake emanates from. But we also have H, which is kind of like the geographical or the three-dimensional place, the exact point that earthquake emanates from, the hypocenter. 4 and 5 are just different modes of building failure. One could be overturning. The seismic activities pull the building from its foundation. The building just overturns, as if a refrigerator falling over. And then the idea with buildings that have maybe stronger foundation attachments or different kinds of stiffness, this idea of building shear, where the building just fractures. Sometimes this happens at concrete column systems within the buildings. 6 and 7 are illustrating this idea of how a building sways during an earthquake event. So we have a bending of the building in a first mode, just a single waveform. And then during different kinds of seismic activities and different stiffnesses in buildings, we have these higher modes of bending, kind of a higher frequency, so to speak. We're not immune to seismic activity in Western New York. In my lifetime, I've felt at least a few earthquakes. I'm pretty sure that anyone has that's lived in this area. And we have the Niagara Falls, that kind of a major fault that created our escarpment. And primarily when we think about earthquakes, we think about California, and specifically Southern California. But this is, if you can see on this graphic map here, it really defines all of California being in a high seismic zone. So a lot of the, any new buildings they do are always under increasingly more stringent codes. And a lot of the activities of architects and construction firms are in retrofitting pre-existing buildings to these kind of more stringent seismic codes that are coming along. Back to the idea of terminology. Seismic terms, not specific to earthquake activity, but the idea of just a waveform. You can think of that motion of the Earth having a waveform. In this case, this is a very simplified waveform. You can see it compared to a real seismic waveform, but we have the concept of the period, the difference between, or the time before the wave repeats itself, and then the idea of its amplitude, the strength of that waveform. Two terms that I always see brought up, especially during like architectural exams, this idea of P waves and S waves. P waves being high-speed seismic body waves, and these S waves being the shear waves, the shake back and forth perpendicular to the direction that the wave is moving. A couple of illustrations. I thought this was, this book that I grabbed this from was really well illustrated. So we have this idea of a mass, something I think we could all relate to. Looks like rabbit ears here, but imagine this is just swinging back and forth with a mass on it after being exposed to the ground plane, moving back and forth. So we have a pendulum type effect. And that's not unlike what would happen to a building when that motion was occurring. And probably the new introduction here is how that kind of spectral acceleration is affected by the kind of soil that the building sits in. So here's some things right out of the IBC tables for site classifications. To the idea what the shear velocity is at the top of 100 feet, so to speak, if we were designing a building that tall, and then the kind of reactions to depending on what kind of soil type the building is in. And then another chart defining the idea of the types of construction and like the idea of how high you can build. So these are code, a lot of this stuff is code defined for us. I probably should leave this one out. This is a little more complicated in far as, and I'm not sure it's very useful to us. The idea that taller building having more distribution of forces towards the top. Really critical, though, is the idea of starting to think about this idea that the shear walls work as a unit with the horizontal diaphragms, the floor planes of a building. And we're introducing two kinds of diaphragms here, a flexible diaphragm and a rigid diaphragm. Flexible being, in this case, they describe it as a plywood sheathing on an ordinary wood-framed building. And then the rigid diaphragm being like a concrete slab or a steel deck, maybe with a concrete overlay on it. And those create stiffer floor planes, and then they have a net effect to the overall stiffness of the building. Another idea in design of buildings is this idea of where we place our shear walls with respect to the center, like the center of mass of the building. So, and then in that case, how stiff and how concentrically the building will like modulate or flex when it's exposed to a earthquake. So we have some kind of, in this case, 5 and 6 are interesting. They kind of outline them. This idea of putting the shear walls on the outside to resist this idea of torsion or twisting within the building. And then, or having the shear walls in the configuration that might be like an elevator core, and that is greater bending resistance because, and let me move my head, walls act together as core and thus provide greater moment of inertia. So greater bending resistance. And building configurations, the shape of the building. So this is an HLU LTU. It's four different kinds of building configurations. But the idea here is these wings can create stress concentrations, illustrated here in the green, places where the building can fracture apart. If it breaks apart, it can then continue to, hit each other and create further damage during an earthquake. So a lot of design goes into this idea of these shapes and how well they are able to resist seismic activity. I think these are good illustrations of the idea of the performance of shear walls, especially during seismic activities. So one, we have narrow shear walls, and the idea is that because they're narrow, they're easily overturned, they're tall and slender. So this kind of an architectural mitigation of making the shear walls wider. Obviously, that has huge amounts of implications for the way we would do layout. So there's a structural concept of the mitigation, and that is to tie those shear walls to the floor decks so that we're working to lock everything together. So how do they describe that? Structural attached to shear walls to the edge beams designed to resist the overturning in the building. So there is the idea that we have this as a preferred design. This is the suggested design for shear wall performance, and this is the engineering fix to that whole problem in order to maintain that same kind of a facade configuration. Another really useful graphic, the engineer building the building on the hillside wants to create a level platform. The architect wants the building to move with the landform or adapt to the landform. And in this case, this also proves out to be more resistant to some of the issues that happen during a seismic event, whether it be in the movement of the soil or just the idea of the need for, or the lack of need for all of this free, unsupported area. And when I say unsupported, this could be still in soil, but the soil could be soft and actually offer no resistance during an earthquake. Now into some of the details, and I have a few more images of these later on, but this idea, and this is specifically to wood framing, but the idea of connections of shear walls and making sure those shear walls perform properly. So in A, we show that the first order is to fasten that shear wall, what will become that shear wall. It's a wood framed wall right here up now in A, to the foundation. 6 foot on center. I think the code is now maybe 3 foot on center for this, for just about any area. But that is to lock that shear wall to the foundation. This is just a B would be a hold down. Maybe in now we don't have a shear wall, but we have a post and beam, maybe a post-in beam or braced beam configuration or a moment frame, but we're still indicating that same kind of hold down to resist that idea of overturning. C is the panel nailing scheme. And this is really critical and something that building inspectors would catch, and something that an architect who might be doing a site visit should be well attuned to also. This is the plywood sheathing on the wall, and this is kind of would be a nailing schedule. So we have this idea of spacing the nailing. Typically the code specify this 6 inches on max along the perimeter. And then they have a term they call in the field, where sometimes that spacing is relaxed to like 12 inches. In D, we show this connection of shear wall to shear wall, the wall-to-wall hold down as we go through floor slabs. And this is another illustration of techniques to tie all of the structure together. So we're using framing anchor clips here. F, just some beam connection details. Once again, the idea of tying these things during seismic events. G, shear wall, the idea of the height to width ratio. This gypsum fiber panel being less strong to resist that kind of a nailing schedule and damage itself. So the code requires it to have a different kind of ratio. And then finally, we have this idea of joist blocking to transfer shear at the panel edges. So just an overview of just kind of what happens when we're into the details of wood framing. Another graphic I wanted to put in, this idea of bracing. We'll go through a couple of other ideas of bracing systems, but this one in the center is kind of interesting because we have this idea of eccentric bracing. The bracing isn't actually touching at the corner points here. It's kind of mid-span. So what we have here is the idea is to stiffen this assembly but not make it too stiff. Less stiffness than a fully braced frame. And this could be to tune the building so that it has some flexibility in it. And then there's another way to kind of support a building without, obviously in addition to shear walls, bracing, and other techniques, in places where the building may actually possibly may not even be able to be retrofitted or be too difficult. The idea of isolating the building from the moving soil. So there's these base isolators. And, I liken it to, I put this graphic over here. Imagine, the classic idea or the joke where you set a table and then you quickly pull the tablecloth out from under it and the dishes stay where they are. The idea here is the earth is moving underneath it, and because of the mass of the building is seeing a much reduced motion within it. So that concludes the first part of this. I'm going to pick it up again in a second. And if you're following along, the first keyword is coffee.